Imagine a time before stars, planets, or even the smallest speck of dust existed. Picture a universe so empty, so silent, that not even the concept of time had meaning yet. There was no light, no sound, and no form, just a vast, infinite nothingness waiting for something extraordinary to happen. This is the starting point for our greatest scientific story, the story of the universe itself, a tale that stretches across billions of years and countless galaxies. Scientists call this origin the Big Bang Theory, a revolutionary idea that changed how we see our place in the cosmos. It wasn't an explosion in space, but the birth of space, time, and all matter from a single, unimaginably hot and dense point. This moment marked the true beginning of everything we know. About 13.8 billion years ago, everything, energy, matter, even the laws of physics, was contained in a singularity, smaller than an atom, yet holding the potential for an entire universe. In an instant it began to expand, space itself stretching, carrying everything with it. This expansion continues even today, shaping the cosmos we observe. This idea is the cornerstone of modern cosmology, explaining how the universe evolved from that first moment into the vast, complex structure we see now. The Big Bang Theory helps us answer some of humanity's oldest questions. Where did we come from? How did the universe become what it is today? What is our place in this grand design? Every atom in your body, every rock, every star, was forged from the energy and matter released in that first moment. The elements that make up our world were born in the hearts of ancient stars, themselves products of the Big Bang. We are, quite literally, made of stardust, created from the universe's initial expansion and the cosmic processes that followed. The story of the Big Bang is our story, connecting us to the grandest scales of existence and reminding us of our shared cosmic heritage. It reminds us that we are part of an immense, ancient cosmic tapestry, woven from the very fabric of the universe itself, stretching across time and space. Picture the universe in its first fraction of a second, a realm so extreme our language barely describes it. Imagine everything you know, every star, planet, and atom compressed into a single, unimaginably tiny point. This was the very beginning, where the laws of physics as we know them were stretched to their limits. The entire observable universe was compressed into a space smaller than a period. It was so dense and compact that even the concept of space and time as we understand them had not yet taken shape. It was a seething soup of pure energy, hotter and denser than anything we can imagine. Temperatures soared to trillions of degrees, and the energy was so intense that matter as we know it could not exist. No atoms, no protons, just fundamental particles and forces merged together. The universe was a chaotic blend of the most basic building blocks, unified in a way that defies our everyday experience. This was the quark-gluon plasma epoch, lasting only millionths of a second. In this brief moment, quarks and gluons moved freely, unbound by the forces that would later hold them together. As the universe expanded, it cooled, allowing complexity to emerge. The intense energy began to settle, and the first hints of structure appeared in the chaos. Inflation followed, a burst of expansion faster than light, ballooning the universe from subatomic to grapefruit-sized in an instant. This rapid growth smoothed out any irregularities, setting the stage for everything to come. Inflation explains why the universe is so vast and uniform. It stretched space itself, making the cosmos appear remarkably even and consistent in every direction. As it cooled further, the fundamental forces separated and quarks and gluons formed protons and neutrons. These particles would become the seeds of all matter in the universe. For the first time, the ingredients for matter appeared. Hydrogen and helium, the simplest elements, began to take shape from this cosmic brew. The universe was still a hot, dense fog, but the stage was set for the creation of the first elements. Light struggled to travel freely, but the groundwork for stars and galaxies was being laid. The cosmic story was just beginning, with the promise of complexity, structure, and the birth of everything we know still ahead. One of the strongest clues for the Big Bang comes from observing distant galaxies. When astronomers peer deep into the night sky, they're not just looking at points of light, they're looking back in time, seeing galaxies as they were millions or even billions of years ago. Their light is shifted toward the red end of the spectrum, a phenomenon called redshift. This shift isn't just a subtle change, it's a cosmic fingerprint, revealing how fast these galaxies are moving away from us. Like the drop in pitch of a receding siren, light from galaxies moving away is stretched, shifting to red. This effect, known as the Doppler effect, helps us understand motion not just on Earth, but across the universe. In the 1920s, Edwin Hubble discovered that nearly every galaxy is moving away from us, and the farther they are, the faster they recede. This was a revolutionary finding that changed our understanding of the cosmos forever. This became Hubble's law, direct evidence that the universe is expanding. The relationship between distance and speed is now a cornerstone of modern cosmology. Imagine dots on a balloon, inflate it, and every dot moves away from every other dot. There's no single center. Instead, expansion happens everywhere at once, just like in our universe. The redshift is the signature of this cosmic stretching. It's a direct measurement of how space itself is expanding, carrying galaxies apart. If the universe is expanding now, it must have been smaller, denser, and hotter in the past. This idea leads us back to the Big Bang, the moment when everything began. By measuring redshift, we can rewind the universe's history back to its fiery beginning. Each data point is like a page in the universe's diary, telling us about its age, size, and evolution. Redshift remains a fundamental tool for mapping the cosmos and measuring its growth. It helps us chart the vast web of galaxies and understand the structure of the universe on the largest scales. It's not just a historical clue, it's how we explore the universe today. Modern astronomers rely on redshift to discover new galaxies and probe the mysteries of dark energy and cosmic acceleration. The expanding universe is written in the light of distant galaxies. Every photon that reaches us carries a message from the past encoded in its color. Redshift is our window into cosmic history, allowing us to piece together the story of the universe from its earliest moments to today. Another key piece of evidence for the Big Bang is the cosmic microwave background, or CMB, a faint glow filling the universe. The CMB is the afterglow of the Big Bang, a relic from when the universe was young, hot, and dense. For 380,000 years after the Big Bang, the universe was an opaque fog. Light couldn't travel freely. As it cooled, electrons combined with nuclei to form atoms, and the universe became transparent. The trapped photons were released, filling space with a brilliant flash, now stretched into microwaves by cosmic expansion. Discovered by accident in 1965 by Penzias and Wilson, the CMB provided undeniable proof of a hot, dense beginning. This ancient light is a snapshot of the infant universe, allowing us to study its earliest conditions. The CMB's tiny temperature fluctuations are the seeds of all cosmic structure. It's a priceless fossil, echoing the dawn of time. The CMB is the universe's baby picture. To study the Big Bang, scientists use powerful telescopes, our time machines to the past. Light from distant galaxies takes millions or billions of years to reach us, so we see them as they were long ago. Instruments like the Hubble and James Webb Space Telescopes reveal galaxies forming just after the Big Bang. Spectrographs split light into spectra, revealing a galaxy's composition, temperature, and motion, key to measuring redshift and distance. To study the CMB, scientists use sensitive radio telescopes and satellites like COBE, WMAP, and Planck, mapping tiny temperature ripples across the sky. These ripples mark where matter began to clump, forming the first stars and galaxies. Particle accelerators like CERN's Large Hadron Collider recreate early universe conditions by smashing particles together at high energies. Telescopes look back in time, accelerators recreate the beginning of time on Earth. Together, these tools let us piece together the universe's history. Our cosmic detective work continues. In the first minutes after the Big Bang, the universe was a furnace forging the first elements. As it cooled, protons and neutrons stuck together. Big Bang nucleosynthesis. In just 3 minutes, the universe's supply of hydrogen, helium, and traces of lithium and deuterium was created. Observations of ancient stars and gas clouds match these predicted abundances, supporting the Big Bang model. For 380,000 years, the universe was a hot plasma. No stars or galaxies yet. Only after recombination, when atoms formed, could gravity begin to shape cosmic structure. Tiny density fluctuations in the CMB became seeds for galaxies. Over millions of years, matter clumped together, forming the first stars. These stars forged heavier elements, scattered by supernovae, becoming the building blocks for planets and life. The journey from pure energy to complex chemistry had begun. The Big Bang's legacy is all around us. The universe is still expanding, galaxies drifting apart. This expansion shaped the cosmos, allowing galaxies, clusters, and superclusters to form. The hydrogen and helium from the Big Bang remain the most abundant elements, fueling stars. Stars convert this primordial fuel into heavier elements, enriching the universe for planets and life. The carbon in your DNA, the oxygen you breathe, the iron in your blood, all forged in stars with origins in the Big Bang. The theory also frames our search for dark matter and dark energy, which make up most of the universe. Only 5% of the cosmos is ordinary matter, the rest is mysterious and unseen. The Big Bang model guides our quest to understand these cosmic mysteries. It gives us a sense of history and our place in the universe's unfolding story. We are living in a special moment, shaped by the Big Bang. The Big Bang Theory doesn't just explain the past, it predicts the universe's future. The fate of the cosmos is a battle between gravity and the outward push of dark energy. Recent discoveries show the universe's expansion is accelerating, driven by dark energy. This means the universe will not collapse in a big crunch but expand forever. In the far future, galaxies will drift so far apart their light will never reach us. The night sky will grow dark and empty, with only our local group of stars remaining. Over trillions of years, stars will burn out and black holes will slowly evaporate. The universe will become cold, dark, and lifeless. A big freeze. This is the scientifically plausible end to our cosmic story. The universe's journey from fiery birth to silent darkness is written in the stars. The Big Bang Theory is more than a scientific model. It's the grandest story we've ever told. It gives us a rational, evidence-based account of our origins, connecting every living thing to a common cosmic event. The theory is a testament to human curiosity and intellect, built on generations of scientific discovery. It shows our power to piece together a history no one witnessed, using logic, observation, and technology. Studying the Big Bang pushes the boundaries of knowledge, inspiring new science and innovation. The mysteries of dark matter and dark energy drive us to keep exploring. The Big Bang gives us perspective. Our planet is a tiny stage in a vast cosmic arena. This knowledge is humbling but also empowering. It encourages us to cherish our world and each other. The story of the Big Bang is our story. By understanding it, we better understand ourselves and our place in the cosmos.